Welcome. This is our experiential learning topic, the green synthesis of nanomaterials for supercapacitor applications. The team is I, Himamshuji, Chetan, and Dhanush Kote.
Coming to the introduction, what are meant by supercapacitors? Supercapacitors are basically known as ultracapacitors or electrochemical capacitors, and the advanced energy storage devices that bridges the gap between traditional capacitor and batteries. They offer unique capabilities in terms of rapid energy storage and release, making them suitable for applications that require high power bursts and quick charging cycles. Unlike conventional charging cycles, chemical reactions, supercapacitors store energy electrostatically on the surface of electrodes, leading to several distinct features. And capacitor stores energy in the form of electric field, where supercapacitor stores energy between ions of the electrolyte and electrode in the double layer of charge. Next slide. Coming to nanoparticles. Nanoparticles are wide class of materials that include particulate substances which have one dimension less than 100 nanometer at least. They can be used to create more efficient batteries, more effective drug delivery systems, and stronger lighter materials. Nanoparticles have many potential advantages, including increased strength and durability, improved electrical conductivity, and enhanced catalytic activity. Next slide. Coming to green synthesis of nanoparticles. Here, the nanomaterial is a revolutionary approach that combines the principle of nanotechnology with eco-friendly and sustainable particles. The method focuses on basically creating nanoparticles and other nanoscale materials, which uses natural, renewable, and non-toxic resources, which minimizes the use of hazardous chemicals and energy-intense processes. The main objective is to reduce the environmental impact associated with traditional synthesis methods while producing functional nanomaterial with diverse applications. The eco-friendly strategy offers several advantages, which includes reduced environmental impact, cost effectiveness, and the potential for large-scale production. Next slide.
Coming to steps involved, the first step is the selection of precursors. So, choosing one eco-friendly and sustainable precursor material is must. So, it should be derived from natural sources such as the plant extracts or microorganisms. The next step is preparation of extracts. So, it is done by using plant extracts, preparing them by extracting bioactive compounds using some appropriate solvents or methods to obtain the necessary reducing and stabilizing agents. So, the third step involved is reduction and nucleation. So, combining the precursor materials with the bioactive compounds from the extract. So, these compounds act as reducing and stabilizing agents, aiding in the reduction of metal ions and nucleation of nanoparticles. So, next one is synthesis reaction. Uh, so, specializing the synthesis reaction under controlled conditions, which might involve controlling temperature, pH, and reaction time. The reaction should be done by controlling the time and pH and temperature. Then the nanomaterial will form and the characterization should be done. So the characterization may be done using X-ray diffraction or transmission electron microscopy known as TEM or FTIR, that is Fourier transform infrared spectroscopy. The next one is purification and separation. So purifying the synthesis in nanoparticles to remove excess reagents, and drying must be done under the specific temperature for some particular time. Then some further steps will be involved like further processing, then testing and evaluation, and the optimizing and the scaling up. So there's nothing but the optimizing the process parameters for improved yield and documentation. And finally, the prepared nanoparticles will be coated to the supercapacitor. This is the last step. Then we included some case studies regarding the use of nanomaterials synthesis by green methods in supercapacitors. The first one is biogenic synthesis of manganese dioxide nanoparticles for high performance flexible supercapacitors. So this was published in the Journal of Nanomaterials and Energy. So by Sun X Hu Xiang etc. in the year 2016. So MnO2 there's manganese dioxide is a well-known pseudocapacitive material with high capacitance, and its incorporation into supercapacitor electrodes enhances energy storage capabilities. So researchers They adopted a green synthesis approach using a microbial extract as a reducing agent to produce these particles. So the synthesis method followed eco-friendly principles. That's green synthesis. So these particles were integrated into flexible supercapacitor electrodes. So these flexible capacitors demonstrated excellent bending stability and high energy density. That is the performance is good. In the second case study, so it is green synthesis of polyaniline wrapped copper oxide nanoparticles for enhanced supercapacitor performance. So it is done by it's published in the Journal of Sustainable Materials and Energy in the year 2022 by Lamba and Singh. So polyaniline. So it's a conducting polymer with high stability and electrical conductivity, while copper oxide, the CEO, nanoparticles exhibits pseudo-capacitive behavior, making them suitable for supercapacitor electrodes. So they synthesis this by Green's method. So this approach involving a plant extract as a reducing agent to synthesize these nanoparticles. So these nanoparticles were then coated to polyaniline through an environmentally friendly process. So the result obtained were the polyaniline wrapped copper oxide nanoparticles were integrated into supercapacitor electrodes. So the resulting hybrid material demonstrated improved specific capacitance and cycling stability compared to conventional electrode materials. So the performance here also they found uh, the supercapacitors having good performance. So coming to some examples of preparation and the results obtained. The first one is zinc oxide nanoparticles. The precursor is collected from the plant. The scientific name of the plant is Hyptis suvalens. Is collected from uh, some Perambalur district of Tamil Nadu. So the process is initially the they were sliced into little pieces after being cleansed with the deionized water, and then fresh leaf pieces were extracted in the reflux condenser for some half an hour, and the extract is cooled. Then the solution was filtered using some filter paper like Watan paper, and gathered filtrate was stored in the fridge for later use. So this uh, zinc nitrate solution was added in the ratio 1:4 to the prepared leaf extract, and the combination was then agitated for some 3 or 4 hours. Then resulting mass is dried some for some 100 or 120 degrees Celsius in hot air oven. So the yellow paste will be obtained, and again it is calcined to produce fine zinc oxide nanoparticles. So this is the process to prepare nanoparticles. Then so here you can see the results obtained from FTIR and other methods. So the bands, these are associated with some NH group, there's amine group or carbonyl group or CH, etc. And the EDX spectrum of biosynthesis zinc oxide particles helps to know the composition. And according to XRD measurements, so they found that the shape is word-side hexagonal form and particle sizes between some 10 to 200 nanometers. These nanoparticles aggregate due to their high surface energy from being synthesized in aqueous media, and perhaps due to densification, which causes a small spacing between particles. And also, they found that the pattern of rings and spots indicating that nanoparticles have a bigger grain size and a more uniform shape. And also, they are polycrystalline in nature. The next one is manganese oxide nanoparticles. So, the precursor material is leaf extract of a plant called Viola betonicifolia. The methods are as similar: cleaning, deionizing, blending, and addition of water, some reactions in particular temperature and pressure, sorry, pH, and later filtration, collection, reaction, and centrifugation. You can see the flow diagram of the uh, process. Then coating it to a supercapacitor. So preparing the electrodes for supercapacitors. Uh, this first step after preparing the nanoparticles is to prepare the electrodes for supercapacitors. Around some 80 degrees Celsius, the combination of DMAC and polyvinyl difluoride was agitated. Then the super PA and activated carbon were added to this mixture. Then in order to create the electrode, the doctor blade approach is used to paste the sludge on the aluminum sheet and dry it outside. So they are dried in the oven for some 1 hour at around 80 degrees Celsius. So the next step is assembling supercapacitors. Here, two symmetrical manganese oxide and activated carbon composites electrodes were sandwiched between an electrolyte impregnated polypropylene separator to create the capacitor cells. So before use, electrolyte was pre-wetted onto the electrodes, and several experimental methodologies were used to evaluate the performance of the supercapacitor. Coming to results, so the inclusion of manganese oxide enhances the composites capacitance by combining the effects of metal oxide's Faraday capacitance and activated carbon's double layer capacitance. And the pseudo capacitance from redox reactions results in improved capacitance, especially evident around 5% manganese oxide composite. And the CV tests analyze the variation in manganese oxide and show well reversible redox reactions with distinct peaks at 0 voltage. Effective electrical and ionic conductivity contributes to the high capacitance achieved by these electrodes. And energy storage in these electrodes involve a double layer of ionic charge at the electrode or electrode and electrolyte interface due to activated carbon surface area and porosity. Also, the CV curves composite electrodes suggest the electrochemical storage mechanism can be explained by the electrical double layer theory. Over to Chetan.
Then coming to silver nanoparticles. Here, the synthesis of silver nanoparticles uses copper chloride. A solution of silver nitrate was made for this purpose in 25 ml of ethylene glycol. Then it is slowly added to a solution of 0.05 gram of copper chloride, which serves as a reducing agent, and 5 to 6 ml of Eg after half an hour of vigorous stirring. Then the solution tint changed to a pale green. The initial mixture of silver nitrate and Eg was then gradually supplemented with the solution drop by drop. The solution color changed to a bluish green from the pale green. Next slide. After that, the 5 ml of Eg was added separately to a weighted amount of PVP as a capping agent while being vigorously magnetically stirred. Then slowly added to a solution of 0.05 gram of copper chloride, 4 to 6 ml of green source neem, which serves as a reducing agent, and 5 ml of Eg after 25 minutes of vigorous stirring. The initial mixture of silver nitrate and Eg was then gradually supplemented with the solution drop by drop. XRD studies of synthesized silver nanoparticles by copper chloride, neem, henna as reducing agents. Next slide. Other nanoparticles. Coming to titanium dioxide. Here, the numerous forms of nanoparticles can arise when organic acids, proteins, vitamins, and secondary metabolites like flavonoids, alkaloid compounds, terpenoids, that and polysaccharide interact. Complexes of carbon nanotubes and titanium dioxide particles must be added to polymeric matrix in order to maximize the device surface area, their electrochemical response, and the electrical response due to the interaction of EDLC and pseudocapacitor effects. Next slide. Then the other nanoparticle is copper nanoparticle. Here, Hemidia and Oxysporum leaves that had been collected were cleaned with tap water to get rid of the dust. The dried leaves were ground into powder in a blender, and the powder was kept at the room temperature in dark atmosphere. The created extract was first vacuum filtered using cellulose nitrate, membrane, and Wattmann filter paper. The filter paper was either used right away or put into storage for later use at 4 to 5 degrees Celsius. Next slide. Then coming to the advantages, coming flexibility and versatility. In flexibility and versatility, the nanomaterials can be integrated into various electrode configurations, including flexible and wearable devices. Their small size and flexible enable the development of lightweight and compact supercapacitors suitable for diverse applications. Coming to better conductivity. Here, the nanomaterial possess excellent electrical conductivity, which promotes efficient electron transfer within the electrode material. This facility this facilitates faster charge or discharge rates and reduces the overall internal resistance of the supercapacitor, enhancing its performance. Improved capacitance. Here, the presence of nanomaterials with tailored nanostructures such as nanowires, nanoparticles, or nanotubes can significantly enhance the electrochemical capacitance or supercapacitor electrodes. This leads to the higher energy storage capacity compared to traditionally materials. Coming to tunability. Here, coming down here, yes, tunability. Here, the nanomaterials can offer in technologies can be integrated with other energy storage technologies such as batteries to create hybrid systems, combine the advantages of both systems and leading the enhanced energy density and power capabilities, and the other two are enhanced charge storage, and high surface area. Disadvantages. Next slide. Coming to disadvantages, and these are the main things like cost, synthesis complexity, scale up challenges, agglomeration and stability, toxicity and health concerns, limited supply and resources, performance variation, etc. Excellent. In coming to the conclusion, basically the green synthesis of nanomaterials for supercapacitor presents a promising and sustainable approach towards developing high performance energy storage devices. By utilizing these natural resources such as plant extracts and microorganisms as reducing agents and stabilizers, that the green synthesis methods reduces the reliance on hazardous chemicals and energy intensive process associated with conventional synthesis techniques. The use of green synthesis in nanomaterials for supercapacitor has many advantages. The green synthesized nanomaterials exhibit excellent biocompatibility, making them suitable for biomedical applications. These nanomaterials improve the scientific specific capacitance, charge discharge rates, and cyclic stability of supercapacitors. Next, next slide. These are the references used. Thank you.
Thank you.